Hello and welcome. In this lecture, I would like to talk about debugging. This is a very important concept that you need to understand. Specifically, you need to understand some of the tools and some of the methods that you can employ to find and fix bugs. So debugging is the process of finding and fixing errors in a program, usually logic errors. And I'm going to tell you the difference between logic and syntax errors. But it can also include compiler syntax errors. It's the entire process. For syntax errors, debugging is understanding what the compiler is telling you. You always want to focus on fixing the first problem detected. I want to go through some of the common compiler errors and warnings that you may get. But one of the things you always want to know about the compiler is that the compiler may give you a number of errors. You always want to focus on the first error because that first error may result in other errors. So it can be very misleading. If you see 5 errors in a program that the compiler is telling you, you might only have one error, and that first error might be causing the other errors. So it's important to always look at that first stop error and fix that one first. Debugging and the process of finding and fixing bugs can be very complex, from finding simple errors to collecting large amounts of data for analysis. It all depends. Sometimes you don't have any information provided with you except logging. And in that case, you have to analyze things. Sometimes you will have bugs that are not repeatable. You can't reproduce it because it happens in such a rare occasion that usually when you have to analyze logs or some variation of that, the ability to debug by a programmer is an essential skill. It's really a problem solving skill that can save you tremendous amounts of time and money. So it's an important skill to learn. It's an important skill to develop. It takes practice. You are not just going to, it's not just going to come to you. There are certain techniques that you can apply and methods that you can apply to make you better at debugging. I know quite a few numbers of developers that are really good at writing software, writing code. They understand the language very well, but their debugging skills are very poor. They may get a bug, and their first inclination to solving that bug is really kind of off track. And again, this comes with practice. You will get better and better at debugging and understanding how to find and fix problems. But it is important, it is something you have to learn as well. The maintenance phase is the most expensive phase of the software lifecycle. The maintenance phase is after you release your product, and you now have to maintain it. Maintain means fixing any new bugs that come in and also adding few new features. So for example, when Windows releases a new operating system such as Windows 10, they are not done producing that software. It's going to be out in the fields for probably 10 years, and it's still Microsoft's responsibility. When any new bugs come in, or they find new bugs for that software to fix it, and that's why they push auto update and they do things like that. And then they will also notice that the operating system will come out new features as the market changes and as technology changes. So maintenance is very important, and as a result, finding and fixing your bugs is very important. Understand though that bugs are unavoidable. All software have bugs. Nobody can write perfect code, and it's not even necessarily about writing perfect code. It's just things change over time. So that may result in bugs as well. You have to understand that just because software has bugs does not mean it's poorly written code. It's kind of unavoidable. So it's okay to have bugs. When you find and fix them, it's even greater because you actually feel like you are accomplishing something. common problems, and we are going to talk about more about specific problems related to C. But common problems when you are trying to debug are logic errors. Logic errors have to do with the opposite of syntax errors. Your code actually compiles, it works, but it does not do what it's intended to do. So there's some kind of logic or intended functionality that's incorrect. Maybe you have an if statement and you are jumping into that if statement on the wrong condition. Maybe you have a loop and the loop is not executing the right number of times, or you are not sorting correctly. Functionality is broken, but the compiler says everything looks good. Syntax error are directly related to the compiler. These are things not following the rules of language. You don't have semicolon at the end of a statement. You don't have ending right parenthesis with the left parenthesis. You are missing a bracket. You are not using the right keyword. Things like that. Syntax errors are usually caught by the compiler. Logic errors are going to be caught by the programmer during the testing phase. Memory corruption is also a common problem, especially in C. If you are not freeing your memory after allocating it correctly, you can have things like dangling references, and you can also have memory issues related to memory that's not being used. You can have memory leaks, performance scalability. This could be a problem where your functionality is intended as it is, and your code synthetically is correct, but it's not very efficient, or you don't have the hardware to support it. So if you are running a server and you don't have enough hardware to support all the requests, it's going to run really, really slow. Or if you wrote your program to work with 10 users, but when it gets a lot of users, maybe it's not as fast because the database gets bogged down, or whatever the case may be, code works, but it's not designed correctly to handle many amount of users, or whatever the case may be. Lack of cohesion. This can be a problem in your code that reduces quality related to your code is doing too much, or function is doing too much. It's not a single focus, or even an application has too much functionality. It has features that are never used. And so this would probably require a redesign, tight coupling. This also has to do with quality of code. This is where you have a lot of dependencies. Coupling is different than cohesion. Cohesion is your single focus. Coupling is where you have dependencies between maybe functions or between objects. We talked about coupling. We talked about global variables. If a global variable is being used in a lot of different functions, it can cause dependencies between those functions. So what you want to strive for when you write code and you are writing high quality code is you want to have very high cohesion and very low coupling. The debugging process. The first thing you have to do before you can find and fix in an error is you have to understand the problem. This is relatable to just don't just dive in and start looking at the code. Sit down with the tester, understand the requirements, understanding what's going on. Because if you don't understand what's going on, you should not even attempt to try to solve it. Once you understand the bug, try to reproduce it, because reproducing the bug can help you gather more information. It's not always possible to reproduce bugs because they may occur in really rare circumstances. So, for example, bugs that have a like or race conditions or even memory corruption may only happen in very specific use cases, and that they may be intermittent problem. And is that the case? And you can't reproduce it, it's going to become harder and harder to debug. If you are able to reproduce it, you can actually gather enough information to fix it. Most problems are fixable. Also, you can have problems with not being able to reproduce problems if you are multi-threaded environment. Problem processes or threading problems, those are also very hard to debug, but definitely try to reproduce it. And you have figured out what the problem actually is in terms of you are able to understand them. Once you are able to reproduce, or if you are not, then you want to try to apply some kind of divide and conquer. You want to try to isolate the bug, simply the problem, because being able to reduce is going to give you information back, but it might not necessarily tell you what part of the code the bug is in. So what you can do to try to simplify the problem is remove parts of the original test case, so that you are not testing too much. You can isolate the problem even smaller by saying, oh, it only happens in this specific situation. You can also comment out code. We talked about functions just having stubs and not have any implementation. Sometimes that employed in testing so that it can limit the problem set. Also, if you comment out code, you are going to have less code where the bug can actually happen. So as you are commenting out code or backing out changes, the bug may go away. And if the bug goes away, that tells you that the code that you commented out may have been causing it. What you essentially want to do, though it is turn a large program into a lot of small programs, either via testing or commenting out. Another common technique is to have unit tests around your code. If unit test fails, that can tell you exactly where the logic or the problem might be in your code. Once you isolate the bug, that will help you find the origin of the problem in the code. The specific code that causing the problem. Sometimes this will employ using debugging tools such as debugger. We are going to talk about a debugger in specifics, but usually depending on what IDE integrated development you use. There is a debugger that come with the IDE, Visual Studio Code or any other IDE. There is also debuggers that can land standard alone. The big important debugger that we are going to use for C programming is called GDB. It's the GNU debugger. It's also integrated very nicely into code blocks or any other IDE like Visual Studio Code. So it's a nice tool that actually are graphical tools in code blocks where you can stop the execution of your program and add in breakpoints. And then as you stop the execution, you can go line by line in your code and look at the value of variables. So you can see exactly what's going on in your code while it's running. It's an invaluable tool. It's so useful. We are going to run through the debugger and visual blocks. I will show you how to add breakpoints. I will show you how to set up watch. So you can look at variables as they change and also then step through the code. After you have identified the origin of the problem, you then have to fix it. This takes a lot of experience and practice. Just because you found the origin of the problem, you still might not be able to fix it just based on your experience. This sometimes includes redesign or refactoring of other code. That especially with scalability problems or performance problems. You may have to redesign to allow your software to be more scalable. So it's not always easy, but just finding the problem and then fixing it, even harder problems like threading or parallel processing, those are even more difficult to fix. But as you write more and more code, this is going to become easier to do. And then lastly, you got to test like crazy, always test many different boundaries, good cases, bad cases, in between cases, to verify that you have indeed fixed the problem. Some of the techniques and tools that are available, one common and very used tool is to use print statement. You can use print statement to basically trace your code. So in C, you can use a printf statement and you can put it at multiple lines in your code to signify where you are. This is also useful when your program crashes. It can help identify where it crashed. As you are adding these print statements tracing through your code, you can add output in the print statement to see the value of variables, because the value of variables may be affecting state and maybe causing logic issues. So just adding print statements is very useful. It can show the flow of execution and it can help isolate the error. Debuggers, as I mentioned, one in the code block GDB, those can monitor the execution of the program. You can stop it. You can run line by line, restart it, set breakpoint, watch variables, and memory. Very, very helpful when trying to diagnose where a problem resides. Log files. Log files are also very useful, especially for bugs that cannot be recreated. You can analyze them at a later date to see exactly what was going on when the bug happened. So this means that you have to provide good logging statements in your code itself in order for this to be useful. So you may create your own log file and then write to that log as the program running, so that if you do have an error, you can send those logs out to developers. We employ this quite a bit at Xerox, because when we encounter issues, we can't always reproduce them. So they may be encountered in the field. We need to be able to access those logs to see what was happening when that bug happened. Monitoring software. There is software that can monitor and have runtime analysis of memory usage, network traffic, thread, and object information. This can tell you if maybe you are allocating too much memory and not deleting it if you have a tool for memory usage. Network traffic that can tell you whether or not you are sending too many packets out or whether or not your software is scalable. If you have an increase in network traffic and you see that your response time is degrading, you can also monitor threads and objects information for parallel processing to see what's going on in certain threads and what's going on other threads. That will help you diagnose any thread kind of problems. Some other common debugging tools that you can employ to find and fix your errors, you can use exception handling. Many programming languages have exception handling. Unfortunately, C does not. An exception handler will actually prevent crashes and do a lot of things at runtime. It does not apply to C, but it's still a good thing to understand. Try catch blocks, things like that. Static analyzers. These are many static analyzers available for C. Static analyzers analyze the source code without the actual executable running. The program does not need to run it, goes line by line and looks at the source code. And as it's parsing the source code, it looks for any known problems. So it can check semantics. It can make sure that you don't have any uninitialized variables. If you are allocating new memory, that you delete it. If you have any dead code where code's not actually being executed, you can delete that code. It also analyzes things like race conditions and deadlocks. We deploy a couple static analysis. Where I work, we have one called Coverity, which is pretty popular. And there is a code sonar tool that we use as well. And we will run this on our entire baseline, our entire source set. And whenever we introduce new files and new code, that tool will be run on that code and we will be able to identify immediate issue with the code as far as uninitialized variables, memory leaks, so forth. It does not analyze syntax. That is what the compiler is for. There is also a number of test suites that run a separate set of comprehensive system end-to-end tests that you can run on your software. Testing is always important, but if you can automate it somehow to run certain tests every time you do a new build, for example, that can be very helpful. And this can actually prevent errors, but also helps diagnose errors as well. Debugging the program after it has crashed, we are going to talk about something called the call stack. This is very useful mechanism to see, especially in a language like C, where you have a crash and all you the only information that you get is something like segmentation fault. When you have that crash, what happens a lot of time, depending on how it crashed, a core file will get generated, and you can analyze the core file to look at the call stack to see exactly where that program dead. It will tell you the line of code where the program dead. And so we are going to learn about the call stack, and as far as analyzing core files, that's more of an advanced technique. But in a C, a core file can be generated and you can analyze. That's a little more advanced technique, but that's another way you can do debugging on your software. What about preventing errors? We know that debugging is finding and fixing errors, but if you can prevent errors, that's even better. One of the ways that you can prevent errors is you can write high quality code. This is really not a focus on many software engineers. A lot of software engineers write the code as the output is correct, then they consider themselves done. But there is such a thing as poor quality code, and you don't want to write that. I have demonstrated some of this during the lectures, but things like using meaningful variable names, very important. Or if you write inefficient code where you are using loops maybe more than you need to, or using an if statement where you don't need to do that, all these types of things constitute poor quality code. If you have a function that's doing 100 other things and it's not cohesive, if you have 5,000 lines in a function, if your code is not recognized in a module fashion, or if you have many dependencies between functions, again, all of this is poor quality code, and you want to strive not to do this. You want to employ techniques where your program is organized. It's easy to maintain, it's highly cohesive, it has low coupling, and you use meaningful variable names. Very, very important. Again, it's very important also because the maintenance phase is so expensive. If you write poor quality code, it becomes much harder to maintain. It's harder to isolate errors, and it's harder to add new features. So employ good high quality techniques when writing your code. Unit test help prevent errors tremendously. Unit tests are executed usually automatically when you compile. Unit test can help avoid regression. That's one of the most important factors. Regression is when you write new code and you introduce a bug on something that was previously working. You broke old code. You don't want to do that. If some software is working and then something new that you did broke it, you want to immediately be notified. And unit test can help do that because unit tests will run on that old code and will say this was working, now it's falling, failing, failing. It also can find errors in new code before it's delivered, because again, they run after you build it and it will immediately tell you something's wrong. There is concept of test-driven development, which is getting really, really popular. This is where you write your text first and then you develop your code after. And the goal here is when you write your first test, your test is failing, and then you write the code to get it to pass. There's a lot of advantages to TDD. It's kind of a reverse way of thinking. Normally, people, when they write code, they write the code first and then the write to test after. But with TDD, it actually gives you a different way of thinking so that you are working in really small chunks and you tend to write very cohesive code and you don't have the code does not have a lot of dependencies. Because guess what, if you are able to test code, it means that the code does not have many dependencies. If your unit test is really large and you are mocking out all these different things, it usually a big indicator that your code is very dependent on other things. So by employing TDD, it forces you to write a very loosely coupled code that does not have dependencies, and it forces you to have your functions be very cohesive. There are a lot of advantages of TDD. You also have you also want to provide good documentation and you want to proper planning. Don't just dive into code and start implementing. Write down your design on paper, utilize pseudo code, plan your code. If you plan your code, you understand the requirement and you have a good thoughtful design, you can prevent many errors. And I have mentioned this throughout the course, but it's very important to have a divide and conquer type approach. Work in small steps and constantly test after each step. Do not write 1,000 lines of code and then say, okay, compile from test. That is not a good approach. Avoid too many changes at once. When making changes, apply them incrementally. Add one change, then test thoroughly before starting the next step. This can help reduces all sort of bugs and it also limits your problem set. So if you do have a bug, you immediately know where it is in the code because you just compiled and you just added that line or a number of lines. Again, I cannot emphasize the importance of debugging, write high quality code and preventing errors. These problem solving techniques will have you a ton of time and make you much better programmer, top tier programmer. So in the next few lectures, I want to talk about some of the common errors that we see in C programming language. Also, I want to talk a little about the call stack. I want to go through the debugger that code blocks provide and introduce you to the menu options and how you can stop and run watches and so forth. And I also want to help identify some common compiler error that you see how to interpret the compiler warnings and errors. Hello, Venkal. In this lecture, I want to talk a little bit about the call stack, what exactly it is and how you can read it to further help debug your program. Stack trace, which is essentially what the call stack is generated whenever your app crashes because of a fatal error. The reason the term stack is used is because it's referring to a data structure that's common in programming. Stack is a data structure that known as LIFO, last in first out. And that's how the data is stored. The last data element that's added is the first one that you retrieve back out. You can kind of think of it if you are eating a stack of pancakes. The first pancake is at the bottom that you add. The last pancake is at the top. When you go to eat them, you eat the last one that was added. And so a stack trace is very useful when your program crashes because it contains information that helps you debug it. So stack trace shows a list of the functions calls that lead to the error. And what will happen is in a program, when you call your main function, that's the entry point. The main function is going to call other functions. Those functions are going to call other functions. And all those functions that get called will be put on the stack. And so what you can do is when a program crashes, the call stack will tell you that with the last function that was invoked in the specific line of code that caused the error. So the call stack contains a lot of good information It will include the file name and the line numbers of the code that causes the exception or the fatal error to occur. The top of the stack contains the last call that caused the error, and there could be nested calls. The bottom of the stack contains the first call that started the chain of calls to call the error, another function, so forth and so forth. And then that last line is detailed. It's very, very helpful when app crashes. And so when a C program crashes, it may generate a segmentation fault. And that does not tell you a lot of information. It just means something bad happened that will also generate a core file. You can analyze the core file which contains the call stack, which will tell you the exact line of code that caused the problem for your crash. So you need to find a call in your application that causing the crash. And the call stack is probably the best way to do this. And you don't always need to look at that core file. You can also analyze the call stack using GDP with a debugger. You can see the call stack inside of code blocks. And I want to show you what this looks like. A programmer is also able to dump the stack trace at any time. So if you do catch an error or you recognize that a fatal error might happen, you can dump the call stack to see what's going on. If you don't actually know when the error is going to happen, you can still dump the call stack to see the current traces that led up to a particular call. When using GDP and especially code blocks, the call stack is going to look something like this. You can access the call stack via the menu when you are running the debugger in GDB, and I'm going to show you how to do this. When we go through the GDB debugger and code blocks, but this is what it looks like, and what you will see here is it has a number and address and then the function. This particular call stack here has a lot of different calls. So must have been doing a lot of different nesting and a lot of different function calls. But at the very bottom of the stack in line 22, it says GTK main. GTK main. That means it executes the main function, and then in lines 21, it looks like it executed maybe statement says main loop run. And then it looks like called a function Gmain context iterate. And inside that function, there was some whenever there was another call to a G main context dispatch function. So there was an iterate function, then a dispatch function, and then the question marks on line 18 mean that there is no debugging information. It does not know what happened there. And that's why when you build your program, you can either build it for release or you build it with debugging information. When you build it with debugging information, it contains extra information when you compile, so that when you run, you can look at call stacks. When you release it, build something for release, the executables a lot smaller and may not contain this information. It may contain more question marks. But this will also tell you if you invoked any libraries, any additional programs, it will call those and will tell you the call stack from there. But what this is showing again is the different nested event for the call. At the very top is what's important because that will signifying what caused the crash. So it looks like in the particular call stack, the inner refresh was causing the problem, and you can see that from line 22 to line 0 that there are many different indications of different code, but the eventually program crashed in line 0 call stack information. So you can trace it back. So if you put a breakpoint inside of a function, you run the debugger on that, the debugger is going to stop at that breakpoint. You can then bring up the call stack, and it will tell you how you got to that line of code. This function was invoked filed before this function, and again it usually will start with the main function. You can also switch to different frames if you are familiar with the stack, with the concept how it's in memory. You can look at different frames, but this is very useful tool to find mainly crashes in C, and it's very easy to read. If you just look at the top and you don't understand a lot about the call stack, you can look at the top and say that's a line of code that caused the crash. So I'm going to go through the debugger and GDB. I will show you how you can bring this up. In our particular case, we don't have a program that crashes, so we are just going to look to see make while programming in C. Some of these you might be familiar with from your previous challenges. You have already actually encountered these errors, but these are the most common types of mistakes. First one is very, very obvious. It's missing a semicolon. Remember that all statements in C will end in a semicolon. If you don't have it there, the compiler is going to complain. So either misplacing a semicolon or missing a semicolon entirely is a really common error. In this case, we are misplacing a semicolon. We have an if statement. We put a semicolon at the end of the if statement, and this actually causes the behavior of the program to be completely different. This will actually compile when you miss a semicolon and you don't even have it included. It will not compile. But in this case, the value of j is always going to be set to 0 because the semicolon on the if statement was placed. So the semicolon is perfectly valid to have it after the if statement. It actually represents the null statement, and therefore you don't have an error by the compiler. But this will cause a problem because will never ever be set to 0. And this type of mistake can be common in looping as well. When you have a loop and you put the semicolon at the end of the for loop, and then you may have a bracket where you don't have the bracket because you will have an error if you have the bracket. Very common. Another one is confusing the equals operator with the equals operator. Specifically mentioned that the equals operator is not comparing strings. So if you use equals when you are comparing strings, that's not valid. It's just going to compare the references. But if you actually mean to assign a value to a variable and instead use the equals, you are going to have a compiler. Now, if you try to compare two items like two integers inside of an if statement and instead you use the assignment operator, you actually don't have a compile error, but that expression is always going to evaluate to true. So when you use the equals and you don't use the equals, this is usually made in if while do statements inside a Boolean expression. And this is valid except it has the effect of assignment to something as opposed to executing something. So in this example, if we have if a equals to it, it's assigning 2 to a, it always set to true because that's true statement. Because you never fail when it doing assignment. And so printf is always going to run what you really mean to do. Here is say if opposed to the equals and then not have a compile error. If you use the equals in the wrong situation, you may have unexpected behavior as well, but you will have a compiler error if you are using it to incorrectly for assignment. But be careful of this with the equals instead of the equals. Omitting prototype declaration. I mentioned that it's really important to always declare your functions at the top of the file before you use them. However, this does not always happen and it's very common mistake. And usually what will happen is you will get an implicit declaration error in the compiler. In this example, if you have square root defined later in the program, then where you are invoking it or in another file and you didn't explicitly declare it, you are going to have some warnings. The compiler is going to assume that the function returns an int. It's always safest to include that prototype declaration at the top for all the functions that you call either explicitly or implicitly by including the correct header file in your program. But when you don't include those prototype declaration, you can have errors. Failing to include the header file that includes the definition of a C program. Library function being used in the program. So in this case, you want to reuse some code. Maybe you have the printf functions. You want to display some output, but you do not include the standard level header files. That's a mistake. And that will be usually told you by the compiler. There will be linking problem with that function. So in this case, we have double answer equals square root value 1. If this program does not include the math.header file, this will generate an error that square root is undefined. It will go try to link the object files. It would not have a math.o and it will say, hey, you are calling the square root, but there is no implementation for it. So make sure you include the correct headers for all of your invocations of functions, especially from the standard library. Confusing a character constant in a character string. So here, if we have text equals inside single quotes, that single character that's assigned to the text, if we have a variable named text and we assign in double quotes, that's a point to the character strings. This is not valid for a single character. For a single character, and this actually we have talked about string constants and assigning them to character arrays. And how you can't do that with the equals and you have to actually do them with the star copy. In this case, when we say text equals a, it's assigning a pointer. And this actually is not valid either. And see, what you would have to do is you'd have to do star text equals or the star copy if you don't want to assign it directly like that. But you get the gist using an inside of single quotes versus a character inside double quotes. Completely different character versus string. In the first case, text is normally declared to be a char variable, and in the second case, it should be declared to be type pointer to a char. And if you want to assign a value to that pointer other than the pointer itself, you have to be reference it. This is actually incorrect because if it's a pointer, instead of assigning an address, you are assigning it a string. So that does not make sense. Using the wrong bounds for an array out of bounds exception, here we are declaring an integer array of 100 size. And then a couple variables I and sum with only some being initialized, and we go through our loop. We say for equals 1 is less than equals to 100. That's incorrect because the size of 100 means that there is 100 elements in the array, but arrays are zero based. So the first element is 0. The max index that you can assign or access in the array is 99. This is because to less than equals. So you are going to have an out of bounds mistake here. This is not a valid subscript because this loop is going to go all the way to 100. It's also probably incorrect because you are starting at 1. If you really wanted the first element of this array, you would start at 0, forgetting to reserve an extra location in an array for the terminating null character of an string. It's also a common problem when declaring your character arrays. They need to be large enough to contain the terminating alone character. This is why I would suggest to you, don't put a size in an array when you create it. If you are initializing it, you would also put the size in there if you are not initializing it. If you are creating initializing on the same line, let's see, do the work for you. It will automatically put the right size and it will include that null terminator. So for example, if you have a character string called hello, this is more than 5 memory locations. It's 6 because of that null terminator at the end. Don't forget about the size of your arrays. This is common problem with pointers, which we have not discussed a ton about, but I did want to just mention because it's very common in pointers when you want to access or even instruct when you want to access something by a pointer, you have to use the dash greater than symbol. That's used when you are accessing a pointer element. So if you have a pointer that's pointing to a structure, that's how you access it. If you have a structure, it's not a pointer, then you access it using a dot operator. A lot of times this dot operator and this dash then greater than is used incorrectly. Dot for non-pointers, pointers dash greater than. This will become clear in more of our examples. Omitting the ampersand before non-pointer variables in a scanf call. So remember, our scanf call expects a pointer as second arguments, and that means an address. When we declare a data type, a variable of type int, that's not a pointer. So in order to allow scanf to store that data in our int variable, we have to pass it the ampersand to say it's an address. So this is incorrect. Not having the ampersand before number and scanf as the second argument is not valid. The only time you do not have the ampersand is if you are using a pointer like a character array. All arguments appearing after the format string and scanf must be pointers. Using a pointer variable before it's initialized. So here's an example of creating a pointer and then trying to assign to it. Then this is the correct assignment where you are assigning a value, you dereference it. But what we have not done here is we have initialized the pointer to actually have any memory allocated for it. And you can't do this in C. You can only apply the indirection operator, which is the asterisk before to a point or variable after you have set the variable pointing somewhere. So it has to be pointing somewhere. Right now it's null. It's not pointing anywhere because you don't allocate any memory. So the char pointer is never set to point to anything. So the assignment is not meaningful. This would actually cause a segmentation fault. Another common error is omitting the break statement at the end of a case in a switch statement. If break is not included at the end of a case, the execution is continued to the next case. So this is what I mentioned, where you have a case, it gets evaluated. And if you don't have that break in there, it does write to the next case and will execute the code inside that next case. So you always want to have break inside your case statement. There are times when you want to have a follow through case to another case, and they do the exact same thing. In that case, you would not have anything inside the case statement. Inserting a semicolon at the end of a preprocessor definition. Preprocessor definition, remember, start with the number, the pound symbol. The preprocessor is run before the compiler, usually for optimization. The correct syntax for preprocessor definition are not to include a semicolon. However, in C, you get into the habit of always putting a semicolon after everything, but you got to remember that if you define some constant data that you don't need the semicolon, this is incorrect. This will lead to a syntax error if it's used an expression like that. So if you actually try to use that to find it, it's going to be okay to have that semicolon at the end, but when the preprocessor runs, it's going to insert exactly what is in that defined. So it's going to serve into end of data 999 colon. This is what the compiler is going to see it, and it's going to actually cause an error. That would be a syntax error. Omitting a closing parenthesis or closing quotation marks on any statement, very common. So this is also directly related to brackets, to having a starting curly brace and then not ending the curly brace. Same thing with parentheses. In this case, we have two starting left parentheses or three, but we only have two ending parentheses. We are missing an ending right parenthesis. That would be a syntax error that the compiler would find. So when you are using embedded in parentheses to set apart each portion of an equation, it makes for a more readable line of code. You want to use parentheses. However, you want to make sure they all match. You start a parenthesis, you have to have an ending closing parenthesis. The same with curly braces. You start a curly brace, it has to have an ending curly brace. So either you have too many or you have too little, but the compiler is going to complain, and this is very, very common. So the second line here is missing a closing quotation mark as well. This print statement, we don't have an ending quote. The compiler will complain about that. Both of these will generate a compiler error. Sometimes though the compiler is very misleading because it does not actually know where the error occurs. It thinks the error might have occurred on a subsequent line. So the line that it tells you the error might be misleading. So depending on whether the compiler uses a parenthesis or a quotation mark on a subsequent line, it will actually complete that expression. So it will move the error down into another line, and that's what it will complain, and that's it where the error is. But the actual error is higher up above where you mean to place it. These are common mistakes that I see a lot of C program making. They are easy to fix, and if you understand them and study this, you will know not to make them. It's okay to make them as a beginner, but as your code get more practice, you will realize I forget a parenthesis, I forget a bracket, I didn't use the equals and equals correctly, I'm using pointers incorrectly, I didn't locate any memory. All these things will come more second nature. Back in this lecture, I just wanted to go over some common compilers and warnings. We talked about some of the common C problems, but sometimes you don't even know you have those errors in your program. When the compiler is trying to tell you that, compiler errors and warnings tend to be really cryptic to new programmers. They may be telling you that you are missing a semicolon, but it says unreachable end of statement. And for somebody new, they might not even know what that means. So it takes a lot of practice and writing a lot of overtime. But I'd like to give you a heads up before that. So some of the common problems that you saw in the previous lecture, I'm going to actually describe some of the compiler warnings and errors and what it will actually say. It's very, very important to tell you to understand what the compiler is telling you. If the compiler is telling you that error, but you don't understand that error, it's going to take you much longer to fix that code. But if you see the error and you know exactly what it's saying, you can then go and fix it in no time. I remember I would be the in the lab, and when I first started programming, and I also be missing a semicolon, semicolon very common, and the compiler would be telling me I'm missing a semicolon, but I would not know that. It would just say unreachable end of statement, and I would be like, what does that mean? What is a statement? I would be very confused. So that's why I wanted to give you some tips on what the compiler is actually trying to tell you. So it's very hard to understand that the compiler is complaining about to decipher these messages. These messages are sometimes very confusing. So you need to understand these compiler errors in order to fix them. Pretty basic, and the compiler is doing half the job for you. It's checking the syntax, telling you exactly what's wrong. So you should use that to your advantage. But sometimes it is difficult to understand exactly what it's saying, especially if you are new and you don't understand some of the terminology. The compiler makes decisions about how to translate your code. There's a common that a programmer that has not written in the code. This is convenient for the programmer and the compiler so that it can be written more succinctly, and also expert programmers take advantage of this feature. So what I am telling you is when you compile, you should always use the dash wall option. This is going to turn on everything. So sometimes a more advanced feature is you will actually take some stuff out, have the translation a little bit more efficient, but when you add that, you cause the program to be compiled differently, and as a result, you may have warning in your code that you don't know about. So the reason I tell you that is you always want to compile with a certain option, which is the dash wall option, and you actually by default that's turn on in code blocks, and this will notify you of all cases where the compiler is doing things that you don't know about. It also will turn on all warnings, give you a lot of information. It's very useful compiler option. Once you have that option on, then you can try to help you better understand some what the compiler is telling you. So the compiler is going to show you two types of problems. One is an error. This will actually prevent the creation of the program. You have a syntax error and the program cannot be compiled. No executable work recreated. And usually when you see errors from the compiler, you always want to focus on that first error. That's the most reliable error, because some of the others error may be a result of that first error. So always focus on that first error, fix the errors at the top first, and then compile again and see if the error go away. Warnings are messages that the compiler shows about for special situations and in which some type of anomaly has been detected. They are non-fatal errors, so the executable will be created, but it is still something that you should fix. A warning is there for a reason. You are either doing something incorrectly or it could cause a problem in the future. So you want to always fix all of your warnings, and by compiling with the dash wall option, you do not consider the program correct until all warnings have been eliminated. So the compilation will not fail. This is why I tell you to use this option as well as seeing everything that's going on by the compiler. So some of the most common compiler messages that you will encounter, and this will be directly related to some of the most common C programs that will be mentioned earlier. If a variable is undeclared, you will see this message variable undeclared first using this function. This is one of the most common and usually easier to detect. And then it will also display the symbol before this message. It will basically say that you are trying to use this variable, but you have never actually declared it. We know that when you declare a variable, you specify the data type. You can't just assigning data to a variable that don't exist. The warning implicit declaration of function, this is related to the function declaration. It's when you are trying to call a function, but if the function does not have any implementation associated, you don't include the header or you didn't declare it, so it does not know where it is and it does not know how the function is declared. It does not know the arguments. It does not know the return value. Has no information about the function itself. To solve this, always declare a function prototype at the top. Another warning, which is it will say warning control reaches end of non-void function. This will happen when a function has been defined as returning a result. It's non-void, but there is no return statement included in the function. So you forgot to return the data. Either the function is incorrectly defined, where you have to remove the data type before the function declaration, or you forgot to add that return statement. One of the other has to be changed in order to fix this warning. But you see how this is a warning. You can still compile there, but man, that could really cause cut problems in your program if you are expecting a function to return something and it does not, so you want to fix your warnings. Unused variables, another common warning. This is printed by the compiler when a variable is declared but it's never used. You should not be declaring a variable if you don't use it, so remove that declaration. I tend to get this quite a bit when I do some of my demos, because I leave in variables that I never use, or when I was demonstrating how to declare a variable and then I compiled it, show you that compiled, I would get a warning saying it was never used. So that's okay, because I was demonstrating something. But remove your variables if they are not being used. No need of declare. Undefined reference to. This happens in the linking phase. So remember the compiler or the compilation phase, it will compile. First, it will run the preprocessor, then it will generate the object files, and then it will take those object files and link them together to make a complete program. So during the linking phase, it needs to resolve any external dependencies or specifically any functions that you are calling. They need to be implemented somewhere. So if it does not have that object file, it's going to give you this problem. You are trying to invoke a function, but we don't have the code for it. So you have to either make sure you link to this file. Usually the link will happen for you, but in GCC, you can just do the -i option to add the linking file. So if you are using a function in the math header file, but you are not linking to the math object file, you are going to get this error. And it also happens if you have user defined and you didn't include a C source file. So you have multiple C source files. One of the C source files is implementing this function. Another C source file is including the header and calling it. But you never compile the other C source file that has the implementation. You will see this error. So make sure you bring in that source file. Make sure you bring in any standard library source file. If you need to explicitly, usually you don't have to do that. Another common error, this is when conflicting types for, this is when you actually have defined or declared a function prototype, and then when you went to implement it, it was not the same as how you declare it. So for example, the prototype has a result type and names of parentheses for the parameters, and then a semicolon, and then you define the implementation. You have a different actual function header, you have a different return type, or you have a different number of parameters. And this is saying, well, hey, you have this one function declaration, and then when you go to implement it down below, it's completely different. So there is a mismatch. And this will actually show you on the link that the conflict appears. In the previous definition that caused the contradiction, so in the implementation is usually where it shows you the line runtime errors. Runtime errors are problems in your code that happens when you run the program, not when you compile it. So these are usually crashed or they are the non-fatal errors. Where you are array out of bounds or something like that, it's when the program is running, you have some kind of logic errors. So the execution of C programs may terminate abruptly with a crash. When a runtime error is detected, something it cannot handle, there is memory corruption. Like I mentioned, out of bounds error usually cause programs to crash. Usually, what you will see is segmentation fault, and segmentation fault does not really tell you anything. So typically what you want to do to further diagnose this problem is look at the call stacks, as I mentioned, before the program crashes, steeping line by line. To see what line is causing the crash, you can get the call stack. If there is a core file, which I mentioned earlier, and then from the call stack, you can see what line is crashing, or better yet, run the debugger step line by line, and then when you execute a line debugger, you will see the program and crash, and you can identify it that way. So these are just again some more tips or compile errors and warnings and messages and how to interrupt them. There is actually links online, or if you do Google, it will tell you every single compiler error and warning that can be produced, and it will actually give a definition of why this was produced, it is, and what was the problem essentially. Because again, those compiler errors can be very cryptic, and even the one word said unreachable control, you know from that description necessarily, unless you had experienced that, that means, oh, you never return something from a function. But if you, one of the best ways to find and fix problems in your program, when you have compiler errors and don't understand that compiler, Google it, and typically what will happen is you will go to Stack Overflow and it will tell you, "Hey, this is your error, this is how you solve it, how do that this day." I have been programming in C for 15 years, but there are still times when I encounter things and I am like, that exactly does this mean, and I googled it. I actually take the compiler, put it in quotes, and it will tell me exactly what's happening. Stack Overflow is really good website, and it can really save a lot of time in the debugging process. Don't just try to guess, and it will pinpoint exactly what's going on. So if you understand, you are going to be able to fix your problem much and much quicker. And if it's not something you are familiar with, go to Stack Overflow or go to website that describes all of them, like Stack Exchange also, and you can decipher it that way, this message. I hope this was helpful. Thank you. Thank you for this session. Thank you for this section. Thank you. You take this course. Definitely you will got more and more from this course.